What's up guys, it's me, Sir Ernest, and today we're going to solve a problem involving coupled oscillators. The problem reads, a light elastic spring of stiffness K is clamped at its upper end and supports a particle of mass m at its lower end. A second spring of stiffness K is fastened to the particle and in turn supports a particle of mass 2m at its lower end. Find the normal frequency of the system for the vertical oscillations about the equilibrium configuration. Okay, so here we have an example wherein our coupled oscillator is configured in a vertical manner. So here we have one particle with mass m supported by a spring of spring constant k, and this particle m is connected to another particle with mass 2m and spring constant k as well. Because of the weights of the particle, the equilibrium position shifts downward. In such a case, the resulting motion would akin to a simple coupled oscillator oriented in a horizontal direction. So in other words, because we are considering the shifted equilibrium positions, the gravitational effect can be neglected because of the shift. So remember when during our last previous discussion that when an oscillator or simple harmonic oscillator is subject to a constant force, just like the weight of the particle, okay, that results to another simple harmonic motion with a shifted coordinate system or shifted equilibrium position. So from there we can now define two resulting coordinates, x1 and x2, where x1 and x2 are measured with respect to the resulting shifted equilibrium position. Okay, so with this, the resulting Lagrangian will now be equal to 1/2 m x1 dot squared. So this is the kinetic energy of the first particle, plus 1/2 times 2m x2 dot squared. This is the kinetic energy of the second particle, and this is minus 1/2 k x1 squared. So 1/2 k x1 squared is the potential energy associated to the upper spring, and then minus 1/2 k times x2 minus x1 squared, where 1/2 k times x2 minus x1 squared is the resulting potential energy due to the spring. So as I mentioned earlier, the gravitational effect is already absorbed, so to speak, to the idea of shifted equilibrium positions. So that means in the Lagrangian, the gravitational potential energy will be neglected or will be removed altogether. So using the Euler-Lagrange equation, we now have the following equations of motion. So the first equation of motion can now be written as the time derivative of the partial derivative of the Lagrangian with respect to x1 dot minus partial derivative of L with respect to x1, and this is equal to 0. So this will yield to the equation of motion mx1 double dot plus 2k x1 minus k x2 equals 0. Okay, so when you apply this Lagrangian to this Euler-Lagrange equation, this is the resulting equation of motion. You can do this even when your eyes are closed, right? So the second equation of motion associated to x2 will be equal to will be expressed in as 2m x2 double dots plus k x2 k x1 equals 0. Okay, so we can solve this. We can solve x1 and x2 in various ways. So in this case, we're going to assume a solution of the form x equals a e to the I omega t, so that x double dot is equal to a sorry, it should be negative omega squared. Good. This should be negative omega squared a e to the I omega t, which is equal to negative omega squared x. Now from here, we can now solve this equation. We can now use this assumption, and we substitute it here and here. Okay, so the first equation would look like negative m omega squared x1 plus 2k x1 minus k x2 equals 0, or negative 2m omega squared x2 plus k x2 minus k x1 equals 0. Okay, sorry, this should be k only. Okay, so these two equations can now be rewritten in this form. The first equation is written as 2k minus m omega squared x1 minus k x2 equals 0. And the second equation becomes k minus 2 m omega squared x2 minus k x1 equals 0, which is written in matrix form as follows. So in matrix form, this is written as 2k minus m omega squared negative k, and then k minus 2m omega squared negative k x1 x2 equals 0. Okay, and the solution to this equation is just the determinant of these 2 by 2 matrix. Okay, so let's do that. So here we now have the determinant of this is 2k minus m omega squared. Oh, sorry, this should be sorry about that. This should be written as, okay, this should be reversed, because remember that k minus 2m omega squared k minus 2m omega squared is for x2, so this should be negative k and then k minus 2m omega squared. Okay, so again repeat, the determinant of this 2 by 2 matrix becomes 2k minus m omega squared times k minus 2m omega squared minus k squared, and then we equate it to 0. From here, we can now solve this equation as follows. So 2k squared minus 4k m omega squared minus km omega squared plus 2m squared omega to the fourth minus k squared equals 0. Okay, so from here this can be simplified as k squared minus 5 km omega squared plus 2m squared omega to the fourth equals 0, which is actually a quadratic equation in k. So if, for example, if we let the variable y to be equal to m omega squared, so therefore this expression can now be rewritten as 2y squared minus 5k y plus k squared equals 0. Okay, so because here we're looking for omega, so our unknown should be y, and therefore we can solve this by getting the quadratic equation. For the quadratic equation, this is now equal to plus 5k plus or minus square root of 5k squared minus 4 times 2 k squared over 2 times 2. Okay, which is simplified to this expression, 5 plus or minus square root of 17 over 4k. Again, this is equal to m omega squared. Okay, so from here we will be able to calculate or express the characteristic frequency or the normal frequency as follows. Omega is now equal to the square root of 5 plus or minus square root of 17 over 4 times k over m. Okay, so these are your characteristic frequencies. Now, if, for example, we choose the first characteristic frequency omega 1, which is equal to square root of 5 plus square root of 17 over 4 times k over m. So therefore, equation 1, what is equation 1? So remember that the first equation is 2k minus m omega squared x1 minus k x2 equals 0. So this becomes 2k minus what? Okay, good. It should be 2k minus 5 plus square root of 17 over 4k times x1 minus k x2 equals 0. Okay, so this yields the relationship between the two, given by 3 minus square root of 17 over 4 x1 equals x2. So this result is actually what we call as in asymmetrical mode. Why? Because actually this term or this number is actually equal to negative 0.281. Okay, so what happens here is if this particle so if these are your two oscillators, M and 2M, so what happens here is when the particle moves, when M moves downward with the amount x1, x2 will move in the opposite direction but with a smaller amplitude, but opposite in the direction. So in other words, the displacement of the lower mass is about 0.281 that of the upper mass, and the direction is opposite. On the other hand, if for example we choose omega 2, if we choose omega 2, which is equal to what? This is equal to square root of, okay, good, this is square root of 5 minus square root of 17 over 4k over m. So again, substituting this, let's substitute this to equation number 2, wherein equation number 2 is k minus, you can also substitute it to equation number 1, but let's choose equation number 2. Okay, so this is k minus 2m omega squared x2 minus k x1 equals 0. Okay, so this becomes k minus 5 minus square root of 17 over 2. Times x2 minus k x1 equals 0, which yields to the relationship between x2 and x1, wherein this is negative 3 plus square root of 17 over 2 x2 minus x1, or simply x1 is equal to x2, but the factor for x1 would be 1.781. Okay, so this result is an example of a symmetrical. And if we're going to illustrate this, this is what happens. So if this is your oscillators, M and 2M, this is K, this is K. So if the particle here, or the upper particle, moves downward by x1. x2 will move downward as well, but with a larger, almost double the displacement. Okay, so the direction of the motion of the two particles are the same. That's why it's called the symmetrical mode. Okay, so in other words, the displacement of the lower mass is 1.781 approximately times that of the upper mass. Okay, so in other words, the magnitude of the displacement for x1 in this mode is less than the magnitude of x2, whereas here the magnitude of x1 is greater than the magnitude of x2. Okay, so that's it. That is the full solution to problem 11.17 of Fowles and Cassiday 7th edition. Okay, so I hope you learned something today. And that's all for now, and I'll see you guys in the next video. Bye bye.